Yo, 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 microbiology! We're doing bacterial metabolism, as you can see, with Doug McD, part 3. So, to review, we got autotrophs. Autotrophs make their own sugar, and then make energy by breaking up that sugar. We got two ways of doing that. We got photosynthesis, and we got chemosynthesis. Photosynthesis with light, chemosynthesis with chemicals. So, we are still working on the heterotrophs, which we have to eat to take in sugar, and then we can make energy. So, we've gone through aerobic respiration with air, anaerobic respiration with no air, and finally we got fermentation, which still goes through glycolysis, but then it goes different. We got glycolysis, and then it can either go to alcohol or lactic acid. So let's check this out. Okay, fermentation. Glycolysis, same old, same old. 2 pyruvates, 2 ATPs, 2 NADHs. Awesome. Now there are a couple ways to do fermentation pathway, or end products. Now, these are our main two. The homolactic acid or the alcohol. These are the normal two. We can have the pyruvate go through the system and come out as lactic acid, or we can have it come out as ethyl alcohol. Normal. Let's take a look at this. So, again, we've got the glycolysis up here. And as we go through glycolysis, we create 2 ATP and 2 NADHs. So, then we got 2 pyruvic acid. Now, normally, if we were doing respiration, if you look up in this corner picture up here, it would go through it and turn into acetyl-CoA, and then, oh, dang it. Keep the colors, change the colors, current color scheme. Keep the color scheme, don't show this message again. Shouldn't happen again. So, here we go. Pyruvic acid can go into the acetyl-CoA and then into the Krebs cycle, but that's respiration. We're talking about fermentation. So, fermentation, it actually comes this side. So, fermentation, we got the 2 pyruvic acids, and it turns into pyruvic acid, then it can form the end products. Again, the most common 2 end products are going to be lactic acid or alcohol. Now, do remember that we do get 2 ATP out of it. So some energy is better than none. So the 2 ways of going through this is we've got the 2 pyruvic acids and we use 2 NADHs. So we use energy to either create lactic acid or to create ethanol, which is ethyl alcohol or alcohol fermentation. Normal 2. This is what normally goes through. Now guys, if you remember in this previous slide here, we said that lactic acid is done by streptococcus or lactobacilli, and the alcohol is done by yeast. Now guys, fermentation is done by a lot more bacteria than this. We have mixed acid fermentation that gives us lots of different acids at the byproduct, and that's done by E. coli and some enterobacteria. We've got butyl glycol fermentation, which is done by Pseudomonas down here, and we've got propionic acid done by the propionic bacterium. Now, okay, C, D, and E. Don't have to know them for sure, but you do need to know that there are more than just 2 types of fermentation. So, to review about the alternative pathways, going back to aerobic respiration, we have to take in organic compounds. So these guys have to be eaten. Part of the carbon is sent over here for carbon fixation to create more sugars. Then, some of the carbon is sent down here for biosynthesis, making macromolecules, lipids, carbohydrates, nucleic acids, and amino acids. Okay, the rest of it, if you remember, the electrons go through that electron transport chain, and with aerobic respiration, we have oxygen as the terminal electron acceptor. Now, remember, with oxygen as that terminal electron acceptor, we've got the most ATP being created. The most. So, total over here, with aerobic respiration, get 38 ATP. 38! That's awesome. So this would be the most efficient pathway to go through, aerobic respiration. Now let's check out the next one. Anaerobic respiration. We still have to eat and take in these organic molecules. Again, some goes over here for carbon fixation to create sugars. Some of the carbon flow goes to biosynthesis, creating of macromolecules. And then for anaerobic respiration, we cannot have oxygen as our terminal acceptor. So, we have nitrates, or sulfates, or other organic acceptors that can take in that electron. Now, what that means is we don't get as much ATP. So, this is a lot less ATP, so a lot less efficient. But hey, it's better than none. Next, we have chemolytic autotrophs, or chemolithotrophs. Again, we're going to take in inorganic substances, so the chemicals surrounding them. And we're going to break those chemicals to give us the electron we need. And that electron's going to go through that electron transport chain and end in oxygen. So what does that mean? Ending in oxygen means a whole bunch of ATP. Good stuff. Now, carbon. They must take in carbon molecules or build them up using the chemicals that are found around their environment. And the use of those are going to biosynthesis, or creation of macromolecules. Okay, the final pathway we're going to talk about, alternate energy generation pattern 4, is the phototropic metabolism. So, light accepts our electron, makes it go through the electron transport chain. Then we've got that proton motive force, passing out those hydrogens, sending them out, so they can come back in, go through that ATPase, and create energy to create ATP. This is good. This stuff creates a lot of ATP. Now guys, you also have to realize that we have to have carbon, so we have to build up the carbon to break it to create biosynthesis, or to create macromolecules. So, the light in the electron is not going to help the carbon. So we have to get the carbon in some other way. And that's going to be either creating it and bringing in chemicals and building it, or we have to take it in through the roots or some other way or some other part of the cell. But it has to come from somewhere. Okay, so overall classes of organisms. All organisms fall into one of these two. They're either going to be phototrophs, which use light. Those are going to be our photosynthetic bacteria. So they can either be autotrophs, which means that they create their own sugars using the light, or they can be photoheterotrophs. They can use photo to create sugars, and they can also get organic sugars brought in. So these guys are awesome here because they can do both. They can use the light to create sugar, or they can just eat sugar, bring it in. Either way, whatever is nice and convenient. So all these other dudes are called chemotrophs. They use chemical compounds as energy. So, first type, where's my mouse? Come on back, mouse. Thank you. First type is organotrophs, using organic chemicals. Okay, remember, these dudes are going to be eating stuff. They have to eat stuff to get the sugars, to break them down, to build them up. So these guys are going to be eating stuff. Now, the chemolithotrophs are a little bit different. They're going to bring in chemicals all on their own. Bringing in chemicals. And there are two types. We're going to have the chemolithoautotrophs, which are going to bring in chemicals and build things up and break them down, all using those chemicals. Second thing is the mixotrophs. These guys can bring in chemicals and build them up and break them down, but they can also actually bring them in and eat them. They can get carbon from other organic sources, so they can bring them in and eat them. So, remember, we are going to be our chemoorganotrophs, but bacteria can be any of these. Okay, Calvin-Benson cycle. I know a lot of y'all were wondering, where the heck is that dark reaction or the actual creation of sugars? So, when we have the Calvin-Benson cycle, we're going to take organic carbon compounds, and we're going to use energy and build up those sugars to store extra energy. Remember, sugars can then be broken down and then release that energy. So sugars are going to store our energy. It is also known as the dark reaction in photosynthesis. So there you go, the dark reaction or the Calvin. But everything does this, including bacteria. This is also known as carbon fixation, fixing the carbon. So carbon fixation. Please put that down even though it's not on my PowerPoint. Carbon fixation. Calvin cycle is carbon fixation. Okay, moving on. So, an example of how this works. We take N carbon, and we do a lot of funky things to it. We have to have the ATP, because we're building things. We're building it. So, we have to use the ATP to actually build and add on stuff. And you know what happens? In the end, we get glucose and sugar. So, taking in the carbon and using the energy to create the sugars. That's what the Calvin-Denson cycle is all about. So, here's a simplified electron transport chain, just as a reminder. So, we get an energy source. One of those energy sources, just kidding. One of those energy sources is either going to be the sun, and we can go through photosynthetic pigments, or it's going to be glucose and other elemental sulfur, ammonia, hydrogen gas, and we have to take those in from the environment. Then, well, what happens? We get ATP as we donate the electrons to our electron carriers. And what happens here is we go through with NADP plus or NAD plus or SAD, and we send the electron to them, which helps create more ATP. And then we end up with the final electron acceptor, or the terminal electron acceptor. Terminal, dude. Totally. So, remember, oxygen is in aerobic respiration. Other inorganic compounds is going to be an anaerobic respiration. And other organic compounds is going to be in fermentation. So, that's all I got today. So let's check this out.
The time has come for this cookie. Nom nom nom. Oh, nom 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 nom. Ah. Bye-bye.
So check it out.